So now let's understand Cook's theorem. But before understanding Cook's theorem, we need to understand what is P, what is NP, and what is NP hard and NP complete. So first let's understand these prerequisites to understand Cook's theorem in a much better way. So there are different kinds of algorithms. Like the algorithm can take O of n time, algorithm can take O of 1 time, algorithm can take big O of 2 power n. Like if you categorize broadly all these algorithms, you'll be getting two major classes. One is polynomial time complexity algorithms. The other is exponential time complexity algorithms. The algorithms whose time complexity is of the form big O of n to the power of k are said to be polynomial time complexity algorithms, and the polynomials whose time complexity is of the form some constant power variable are called exponential algorithms. Examples of polynomial time complexity algorithms could be linear search, binary search, as you can see, insertion sort, merge sort. All these algorithms are taking polynomial time. But when it comes to exponential time algorithms, as you can see, 0, 1 knapsack, which takes 2 to the power of n. Traveling salesman, this is not exactly 2 power n, it is n square into 2 power n, but it can be reduced to 2 power n. Yeah. And graph coloring problem, which also takes 2 to the power of n time. Now, you have understood that what are polynomial time complexity algorithms, what are exponential algorithms. Now we'll see the two important classes. One is P class, the other is NP class. What exactly do we mean by P class? P class consists of set of all deterministic algorithms which run in polynomial time. So I have used a word called deterministic. What does it exactly mean? Deterministic algorithm is that you know each and every step. Yes, you know each and every step in the algorithm, and each and every step is properly defined. This is very important. Each and every step is properly defined. So if an algorithm uh, has every step defined and every step understandable, then that is deterministic. And if it is running in polynomial time, then that particular algorithm falls under P class. That particular algorithm falls under P class. Now let's see what is NP class. NP class means the algorithms which run in non-polynomial time. What does it mean? Non-polynomial time itself means that the algorithm takes exponential time. The algorithm takes exponential time. So this algorithms which are taking exponential time are subcategorized into NP hard and NP complete. We will understand NP hard and NP complete at a point later in time, but first let's understand why are we writing like why are we writing these non-deterministic algorithms? See, for example, if I take 0, 1 knapsack problem, this 0, 1 knapsack problem can be solved in big O of 2 power n time. But at some time in future, at some point of time in future, if the same problem can be solved in polynomial time, if the same problem can be solved in polynomial time, how would it be? Yes, it would be much more efficient because we don't prefer exponential time problems because it always explores all possible combinations. So it would be much better if we are able to convert this exponential time complexity problems to polynomial time complexity problems. For that, we write some algorithms called non-deterministic algorithms. These non-deterministic algorithms help us to preserve our work for future researchers. For example, I'll be explaining you with example. As you can see, there is a search algorithm. As of today, as of today, the best search algorithm that we know is binary search algorithm, which takes big O of log n time. Suppose in future, if someone wants to convert this binary search which takes big O of log into big O of 1. How he will be able to do it? Let's see with an example. Now let's understand this with an example. Suppose we need to find the index of an element in an array of length n. How do you do that? Well, you can use a linear search. Rather, you could use a binary search for better optimization if it is a sorted array. But if I want to write a non-deterministic algorithm for finding an element in an array with big O of 1 time, how will I write that? Though I don't know what exactly happens behind the scenes, just I want to write the brief overview of how it is working. Like, see this example. There is an array. This is the index, like, or we can say this is the answer. This check array is a function which takes this key and the array. It finds out the index of this element in the array. For example, there is an array. There are few elements in the array, and suppose our key is 3. Once the array and key are passed through the function, the output would be 1 because 1 is the index at which 3 is lying. Why I'm saying this is non-deterministic algorithm? Because I'm not knowing how this check array is computing and getting out this index. Yes, you heard it right. I don't know how it is working. Like, this method is not exactly defined, and that is what you call it as non-deterministic. A non-deterministic algorithm is an algorithm which contains few deterministic steps and few non-deterministic steps. At a point later in future, if someone knows how to calculate this index in O1 time, he'll be just filling out it. He'll just define this function. And later, at some point in time, this non-deterministic algorithm will become deterministic, and that is what this circle represents. As you can see, once we found it, we write it and success. Write, success, failure are three important terms. Like, you can see from here, the non-deterministic algorithm uses the three following functions. Choice is arbitrarily chooses one element from the set. Failure indicates an unsuccessful completion. The successful completion of a non-deterministic algorithm makes it deterministic. Remember this point. Now let's understand what does this diagram depict. As you can see, the deterministic algorithms that we know today, the deterministic algorithms that we know today are part of non-deterministic algorithms at some point back in time. That is, all the problems are coming under NP. But the problems that we know today, which run in polynomial time, comes under P. And today, whichever is non-deterministic, that is, whichever is outside of P, at some point of time in future, all these algorithms will be coming into P. That is, all the non-deterministic algorithms at some day will be becoming deterministic. This is what exactly this diagram depicts. From this diagram, we can easily conclude that P is subset or equal to NP. That is, at some point, this P circle, or rather we can say this P subclass expands and becomes equal to NP. And this is what Cook's theorem states. We'll understand it later. As we have seen the relationship between P and NP, now let's try understanding, can we convert all the non-deterministic algorithms which run in exponential time to polynomial time algorithms? Yeah, the answer is yes. If someone brilliant knows everything and he can convert these non-deterministic algorithms which run in polynomial time in exponential time to deterministic algorithms which run in polynomial time. But this is where the problem arises. If you don't know the exact solution, if you don't know the exact solution to run this particular exponential problem in polynomial problem, you at least try to relate it. And what do you mean by relation? Either you solve the problem or you relate it. And for relating the problem, we have to write non-deterministic algorithms. And how do I write? I'll be explaining you. So if you are unable to solve these exponential time algorithms in polynomial time, then at least show some sort of relationship between them, such that if one problem is solvable, that is if one 0 by knapsack is solvable in polynomial time, then all other problems can also be solvable in polynomial time. And for that to happen, we need a base problem. We need a base problem. And this base problem is nothing but satisfiability problem. Yes, you heard it right. It is satisfiability problem. And what exactly is satisfiability problem? Okay, let's understand satisfiability problem by an example. Back in 2-1 in MFCS, you learned about conjective normal forms CNF. Conjective normal forms are generally formed by conjunction of disjunctive normal forms. Like if there are three variables x1, x2, x3, I'm writing an example of CNF. In middle, you will be having the symbol of and between or. So x1, x2, x3, x1, x2, and x3 bar. Satisfiability problem means that for some values of x1, x2, x3, this propositional logic returns a value of true. That is what exactly satisfiability means. If we want to see what exactly satisfiability is, a propositional logic formula Q, this is formula Q, is called satisfiable if there exists some assignments to x1, x2, x3 to its variable which returns its value as true. What all values x1, x2, x3 can take? 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, this is 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. It means that there are 8 possible combination, or rather if there are 3 variables, 2 to the power of 3 combinations are possible. It means this particular problem is an exponential problem. This particular problem is an exponential problem which is successfully terminating with these inputs. There exists some x1, x2, x3 such that it returns true for this particular CNF. Now, why did I say this actually? I said it because to understand NP hard and NP complete, you need to understand what is SAT. So, in simple terms, if I want to say what is SAT, SAT is a Boolean satisfiability condition where there will be some set of variables and you need to assign those variables certain values. The outcome based on your assignment, if it is true, that is satisfied. As you can see, now let's understand about reducibility. This is very important to understand what is the concept behind NP-hard. Reducibility simply means that a way of showing relationship between problems. Yes, you heard it right. Reducibility is a way of showing relationship between problems. Suppose if you go up, there is zero-hour knapsack problem. At this point of time, I'm not able to solve zero-hour knapsack problem in polynomial time. But but if somehow I was able to reduce this zero-hour knapsack problem into satisfiability problem in polynomial time. Remember, this conversion should happen in polynomial time. If it is exponential, there is no point of converting it. If somehow I was able to convert this 0-1 knapsack problem into satisfiability problem in polynomial time, then I'll be saying that this satisfiability problem, if it is solved in polynomial time, then the 0, 1 knapsack problem can also be solved in polynomial time. You may get confused, but let's understand it in detail. Reduction, as I said, reduction is a way of showing relationship. For example, if I was able to reduce satisfiability problem into, or rather 0, 1 knapsack problem into satisfiability problem, or satisfiability problem into 0, 1 knapsack problem, by taking an instance of satisfiability problem which is I1 and converting that instance into some instance of 0, 1 knapsack problem I2 in polynomial time. And what does it mean? In previous case, I have drawn and shown a conjective normal form example which runs in exponential time. If I draw a state space tree for that problem, it looks something like this, like taking x1 as 0, taking x1 as 1, then x2 as 0, x2 as 1, x2 as 0, x2 as 1, similarly x3 as 0, x3 as 1, x3 as 0, x3 as 1, x3 as 0, x3 as 1, similarly x3 0, x3 1. You found a similar state space tree for 0, 1 knapsack problem as well. Suppose if I remove all these problems and ask you, this state space tree belongs to which problem? Will you be able to classify it for a SAT problem or 0, 1 knapsack? No, right? So this is what exactly relationship means. If you are able to solve one NP problem, then all the NP problems can be solved by reduction. Yes. If some problem can be reduced into satisfiability problem, and satisfiability problem is NP complete, then all the problems can be solved which are in NP. Now let's understand what is NP hard. NP hard means it is the toughest problem which we are unable to solve, or which takes a very large amount of time to be solved. If we are able to relate that particular problem Q, let's say Q is NP hard problem. If we are able to reduce that Q to a satisfiability problem, in polynomial time, and we know that SAT can be solved because SAT is NP complete, and hence this problem Q can also be solved in polynomial time. So if we are able to write some non-deterministic polynomial time algorithm for this problem Q, then it becomes NP complete. What is NP complete? NP complete is nothing but NP hard plus NP. What does it mean? It means that you need if you are able to reduce some problem to satisfiability problem, and you are also able to write some non-deterministic algorithm for this particular problem, then this problem falls under NP complete class. Let's understand this with a diagram. Having seen what is NP hard and NP complete, let us understand these concepts with the help of a Venn diagram. So this is the Venn diagram of NP, NP hard, P. Now let's take an example of some particular problem. Let there be a problem L which can be reducible to satisfiability problem in polynomial time. It means that this particular L falls under the category of NP hard because NP hard follows transitivity. That is, if a particular problem L1 is reducible to L2, and if L1 is NP hard, then L2 is also NP hard. And if L2 is reducible to L3, if L2 is NP hard, and L3 will also be NP hard. This is a transitivity property of NP hard class. So we have seen that if a problem L can be reduced to satisfiability problem under polynomial time, it falls under NP hard. And if this particular problem L also has a non-deterministic algorithm which runs in polynomial time, then the combination of these two makes this problem L to fall under the category of NP complete. And hence this SAT is NP complete. since L was NP-complete. So this intersection region represents that all the algorithms fall under NP-complete. So SAT falls under NP-complete. Having seen what is NP-hard, what is NP-complete, now let's try to understand a brief overview of what exactly this Cook's theorem is saying us. See, the deterministic algorithms, that means the elements which are in P, are once upon a time part of NP. Once upon a time a part of NP. All the deterministic algorithms that we know today were non-deterministic at some point back in time. Similarly, all the non-deterministic algorithms that we know today will be coming into deterministic phase as well. That is, the circle of P keeps on expanding, keeps on expanding, keeps on expanding, and at some point time in future, P becomes NP. It means that all the non-deterministic algorithms are solved and defined and converted into P class. Similarly, uh, if this happens, I can surely say that satisfiability problem also belongs to P. Yes, because if this circle of P keeps on expanding, keeps on expanding, keeps on expanding, obviously satisfiability falls under P. And if satisfiability falls under P, all the problems which are reducible, to satisfiability can be solved in polynomial time since satisfiability belongs to P. All the problems which are reducible to satisfiability problems can be solved in polynomial time since satisfiability belongs to P. Okay, now you understood what exactly is Cook's theorem. Stating that Cook's theorem is stating that P is equal to NP. P is equal to NP is happening only if satisfiability belongs to P. Or rather, I could say that satisfiability belongs to P if and only if P is equal to NP. That is, all the non-deterministic algorithms convert to deterministic algorithms. Now, in exam, if you want to write state Cook's theorem answer, then how should you be writing? I'll take an example. Let there be two problems, Q1 and Q2. Q1 problem is solved using some algorithm A with some input I1. Q2 problem is solved with some algorithm set with some input I2, where A is a non-deterministic polynomial time decision-making algorithm. I repeat it, non-deterministic polynomial time decision-making algorithm. This is A. What is Z? Z is a deterministic algorithm. Z is a deterministic algorithm. I say that Q1 is satisfiable. Q1 is satisfiable if and only if A has A has successful termination. A has successful termination with input I1. It means that if I was able to successfully terminate the program with input I1 using this non-deterministic polynomial time decision-making algorithm, then I say that Q1 is satisfiable. And by the property of transitivity, if Q1 can be reduced to satisfiability, and Q1 has some non-deterministic algorithm, then we call Q1 as NP-complete. And thus this satisfiability can be solved in polynomial time, and hence Q1 can also be solved in polynomial time complexity. So in simple words, we'll go through Cook's theorem by the points noted here. Cook's theorem shows that Boolean satisfiability problem means there are some variables x1, x2, x3, and by assigning some Boolean values to these variables, the output has to be true. This is called Boolean satisfiability problem, is NP-complete. To connect this P equal to NP, here is a logical reasoning you have to provide. Cook's theorem states that SAT is NP-complete Yes, we have seen why SAT is NP-complete. That means that SAT is one of the hardest problem in NP. Yes, if SAT can be solved in polynomial time, if SAT can be solved in polynomial time, then all the problems which are reduced to SAT can also be solved in polynomial time. Yes, and thus making P is equal to NP. Now let's take some logical equivalence to understand this. Suppose I take SAT belongs to P. I'm assuming that satisfiability is in P. By the definition of NP completeness, every problem in NP can be reduced to SAT in polynomial time, obviously. And if SAT can be solved in polynomial time, then the solution to every NP problem can also be derived in polynomial time. Yes, and therefore P is equal to NP. It means that this is NP, this is P, this is NP hard, and this is where satisfiability is there. It is telling that satisfiability will belongs to P. It means the P may be intersecting with satisfiability as well. Satisfiability belongs to P only if all the non-deterministic algorithms are deterministic. It means this P keeps on expanding, and at some point time in future, this P becomes NP. So, in one word, if I want to define Cook's theorem, it simply states satisfiability will be in P only if P is equal to NP. This is very important. And in exam, if you get this question, you need to write all these things and you should explain with an example by, like I said, Q1, which takes which uses a non-deterministic polynomial time decision making algorithm with input I1. On successful termination, then this Q1 is said to be SAT, and if Q1 is said to be SAT and having some non-deterministic algorithm, we'll say that this can be run in polynomial time and hence it is NP complete. So remember one line for Cook's theorem: if SAT belongs to P, then P is equal to NP. Hope you understood what is a brief idea. I'm not going into depth of Cook's theorem because Cook's theorem internally uses Turing machine, Turing machine programs, Turing machine programs. If you want detailed overview, go and watch this video on YouTube. It is the best explanation, best mathematical explanation you can see. If you really have time, really have interest, go and watch this Cook-Levin's theorem in examination. You can also ask to write Cook-Levin's theorem. It is as same as Cook's theorem. In this video, we will be explaining full proof how SAT is NP complete by taking examples. So thank you. Thank you for listening.